Okay, in this next lesson, we're going to get into our next kind of topic, which stems from parallel lines, which is quadrilaterals. And you'll kind of see the connection before we're finished with the lesson today. You can see we have a lot of targets. I can recognize and name polygons. So in general, we just want to talk about what a polygon is, because that's what we're going to be working with. I can identify and define special types of quadrilaterals. So we're going to get some nice ones that I know you've heard of before. I can explain the relationships between them. So a lot of them have connections, have commonalities. And then I can identify properties of special quadrilaterals, and I can apply those properties in proofs and to solve problems. So we're going to start out just real general. I've given you some pictures here of polygons and non-polygons. I do need to add a vertex right here on this one, otherwise that would be a polygon. So putting that there, looking at the two different categories of what I've categorized as a polygon and not a polygon, it says describe a polygon based on the above. So I'm kind of going to look at the not examples, like this example right here. Notice this is curved. So I'm going to say it can't have curved sides. All of these must have straight sides. That would be one thing that we know about polygons, right? If you keep looking in this next one, right, this one has sides that cross. Notice we don't have that anywhere. So let's say sides cannot cross, or intersect would be a better word. Right? What's wrong with this guy down here? Right? See how it's open? Right? All of these are, we're going to say, closed figures. So let's just use the word closed. This one, notice this vertex right here has two segments. All of these vertices are like that. They each have two segments that come out of it. But look at this vertex right here. It has 1, 2, 3. That's the problem with this one right here. So maybe we could say each vertex only has two sides stemming from it. And this one is the last kind of scenario I put here. I put a vertice right here in the middle, and we would say these 3 points right here, or these 3 vertices, are collinear. That's a problem, right? So this point right here, it becomes the issue. So we would have to say, how about something like consecutive sides? In other words, this side and this side cannot be collinear. Okay, so to name a polygon, just like we name a triangle, you're going to name the vertices, and they have to go in order. You can start at any one you want, but you have to go clockwise or counterclockwise. So I could not do B, E, C, A, D. That would not be a good example. But I could do A, B, C, D, E. I could do A, E, D, C, B. I could do C, B, A, E, D. All right, so I'm going to say start with any vertex and then name clockwise or counterclockwise. It does not matter. Just so you're moving around in one of those directions. All right, so we want to specifically not just talk about polygons in general, because they're not as exciting, but if you turn the page, you're going to see some names that you have seen before. All right, so a quadrilateral, even if that one's not as familiar, I'm thinking just based on this word quad, you should know what that means. It's specifically a polygon that has 4 sides. So we're going to say if a polygon has 4 sides, then it is a quadrilateral. So it is still a fairly generic term. You could draw any 4-sided figure, and that is a quadrilateral. We really soon want to start talking about these specific cases that you see below. And the biggest one is this really long word here, which I know you've seen before, is a parallelogram. Obviously, a big piece of that is the word parallel, which is what we've been studying. A parallelogram has these 2 sides parallel and has these 2 sides parallel. Thus the word parallelogram. So it is a 4-sided figure, so I'm going to say if a quadrilateral has both pairs of opposite sides parallel, then, and I'm just going to use that, it's a parallelogram. Okay. Now a rectangle is kind of a very specific case of this, right? And I know if I asked you to draw a rectangle, you could all do it, right? So the big question is how is a rectangle different from a parallelogram? Well, not entirely different because the opposite sides are still parallel. So that part is still true, but what makes a rectangle unique is that these angles are right angles. And as soon as you have one right angle, you actually know that they are all right angles because these would be same side interiors. So if this was 90, this would have to be 90. These would be same side interiors, so they would be supplementary, which would force this one to be 90 and likewise. So really you only have to state that it has to have one right angle because one right angle guarantees four right angles. So we're going to say if a parallelogram, we're starting with that, has one right angle, then it's a rectangle. Okay, so it's a special case. Again, one right angle, I'm going to put here, guarantees all right angles from what we know about parallel lines. All right, a rhombus, this one might not be quite as familiar, right? I'm going to draw one for you first. It kind of looks like, because it is a parallelogram, but it also has one unique feature. It doesn't have the right angles, but a rhombus has all these sides to be congruent. So it is also a parallelogram, so we're going to say if a parallelogram, now watch the way I say this, has two consecutive sides congruent, then it's a rhombus. Well, consecutive would mean right in a row, so why am I only saying it would have to have like this side and this side, these two right here? Well, the trick is on a parallelogram, opposite sides, we're going to learn in a moment, have to be congruent. So if these two are congruent, but yet opposite sides are congruent, by transitive we'd get them all congruent. So once again, two consecutive sides guarantees all sides are congruent. All right, but we only really have to have two consecutive sides, not two opposite sides, but two consecutive sides. All right, a kite, I'm sure you've seen that before. Often to draw a kite, easiest is just to kind of make a cross and then connect. Right? I know you can guess what we know about a kite. We know those two sides are congruent, and we know these two sides are congruent. Hopefully you realize I'm not going to start with the words if a parallelogram, because this is not a parallelogram. So we're going to start with if a quadrilateral has two distinct pairs of consecutive congruent sides, then it's a kite. Again, the word consecutive meaning right next to each other. So here's one distinct pair. They're right next to each other. Here's another distinct pair, right? These sides are not involved in the congruences. This pair is congruent and this pair is congruent. That's what kite means. A square, I probably should have put this one before kite. I know you all know what a square looks like. We're back to that parallelogram family because this is most definitely true, right? What else do you know about a square? Right? Hopefully you realize it also has right angles. Right? And finally, there's something else important about a square. Don't we know that all the sides are congruent? So if you think about the ones we've listed above, it's definitely a parallelogram. But much like a rectangle, doesn't it also have right angles? And much like a rhombus, doesn't it also have all sides congruent? So to define a square, we say if a parallelogram is both a rectangle, meaning it has right angles, and a rhombus, meaning all sides are congruent, then it is a square. A trapezoid, I know you've seen this before too. All right, looks something like this. If you've forgotten, a trapezoid is a quadrilateral, but it simply has just one pair of parallel sides. All right, we usually call these the bases. We call these the legs. Little vocabulary there. So we say if a quadrilateral has one pair of parallel sides, then it's a trapezoid. Isosceles trapezoid is the same idea. We have a trapezoid, so we have those parallel lines. But in isosceles, right, you think of an isosceles triangle, it has two sides congruent. An isosceles trapezoid, these legs are congruent. So we're going to say if a trapezoid has the, we'll call them the non-parallel, I'm going to call them legs or sides congruent, then it is an isosceles trapezoid. So let's look over on this page and see if we can kind of fill in these families here in this graphic organizer. Quadrilateral goes on top because that is the family that all of these are under. Everything we talked about on that previous page is a quadrilateral. Think about parallelogram, right? Which one has the most underneath it? Hopefully you can see it's this one right here. So that's where we're going to put parallelogram. All right, now think about what are the two distinct cases of a parallelogram that just have one unique property. That would be a rectangle is one form of a parallelogram that has right angles, and a rhombus is another form of a parallelogram that just has congruent sides, all of them. Now, which one of those is both a rectangle and a rhombus, but a square? Okay. Over here, I'm going to put trapezoid, and then a special case of a trapezoid is an isosceles trapezoid. And then the only one that's missing is kite. And this is kind of an interesting connection sometime, right? We don't often think of that a rhombus is a special case of a kite, right? But if you go back and you think about a rhombus, I'll draw one right here. All right, that's a rhombus. Can you see how that's a special case of a kite? These two are congruent, and these two are congruent. So it is a kite where both distinct pairs are also all the same. So that's that connecting link right there. A rhombus is a special case of a kite where all the sides are congruent. All right, so what we've done on this next page is we've drawn for you parallelogram, a rhombus, a rectangle, a square, a trapezoid, an isosceles trapezoid, and a kite. And on the page right next to it here, we've listed all of those special quadrilaterals that we want to talk about, and we've also listed a bunch of properties here. Equilateral, right? All sides congruent, all angles congruent, and then you see opposite sides parallel, etc. Right? So what we want you to do right now is to pause the video, and we want you to look at these diagrams right here, and just by looking and making good guesses, I want you to see if you can put checks in the boxes. So I'll start you off, right? If I'm looking at a parallelogram, all the sides are not congruent, nor do all the angles look congruent. I know the opposite sides are parallel. The opposite sides certainly look congruent. If I'm looking at opposite angles, right, does this angle look congruent to this angle? I kind of think so. How about this guy and this guy? My guess would be yes, so I would put a check there. Pair of consecutive angles supplementary. I think I know that if these two are parallel and this is a transversal, don't these two angles have to be same side interiors or supplementary? That would be true on all of them. Perpendicular diagonals, doesn't look like it, so I'm not going to check that box. Diagonals bisect each other. I'm looking at the figure. That certainly looks to be true. Congruent diagonals. You get a ruler out, but this one looks to be shorter than this one right here. So I'm going to say no to that. And diagonals bisect the angles. I'm going to say no to that too, because this angle right here does not seem to be as big as this angle right here. So I'm going to leave that bottom one off. So go ahead and pause right now, and just by looking, see if you can fill out the remaining columns. So go ahead and pause and try that. When you come back, we'll do it together. All right, so for a rectangle, right, a rectangle is not equilateral, but it is equiangular because they are all 90 degrees. So let's add that in there. Opposite sides are parallel. Yes, because it is a parallelogram. Opposite sides congruent. Opposite angles are congruent. Consecutive angles are supplementary. Sure, because they are all 90. The diagonals are not perpendicular. They do bisect each other. And this time, if you look closely, the diagonals are congruent, but they do not bisect the angles. In a rhombus, it is equilateral. That is true. It is not equiangular. The opposite sides are parallel. The opposite sides are congruent. The opposite angles are congruent because, of course, it has to have the same properties as a parallelogram. Consecutive angles are sup. The diagonals are, in fact, perpendicular on this one. So you might want to go over that and even mark that in here. That is true. Diagonals bisect each other. That is true because it's part of the parallelogram family. The diagonals are not congruent. The diagonals do, however, bisect the angles. That is true on a rhombus. Now, a square should have been easy to do because remember, a square is both a rectangle and a rhombus. So anything that's true in either one of these columns, right, is also going to be true of a square. So it is equilateral, equiangular, opposite sides are parallel and congruent, opposite angles are congruent. By the way, we should also put in here 90. You could say those angles are right angles. Consecutive angles are sup, the diagonals are perpendicular, they bisect each other, they are congruent, and they bisect the angles. So a kite meets every one of those, not a kite, a square meets every one of those properties. If you looked at a kite, we have a whole lot less going on here in a kite. So the only property I think you should have had is that the diagonals are perpendicular. We'll talk about some other special properties of a kite in a minute. Trapezoid, we have pair of consecutive angles supplementary. So we do have that, right, in a trapezoid. We also have that in an isosceles trapezoid, a pair of consecutive angles that is supplementary. And in an isosceles trapezoid, you also should have had congruent diagonals. All right, now there are some properties we didn't list that are unique to kind of these last three that I want to list down here. In an isosceles trapezoid, I'm going to draw you one. We know it's a trapezoid. We know these legs are congruent, right? We also have base angles congruent. We're going to call those lower base angles and upper base angles. So lower base angles congruent, upper base angles are congruent. And then, of course, I didn't list it up here, but we know that one pair of opposite sides parallel. That comes from that definition. So additional properties of kites. All right, let's draw one here. We said that this is perpendicular here, right? But this diagonal also bisects this one right here. So we can say one diagonal is the perpendicular bisector of the other. Okay, and I realize I'm not on the screen. I apologize. So again, we're looking at the diagonals. We knew that they were perpendicular, but this diagonal does get bisected. So the one diagonal bisects the other diagonal. We do have one pair of opposite angles that are congruent. It's this pair would be congruent to this pair. So one pair of opposite angles are congruent, and we can see that because there's symmetry. This triangle would have to be congruent to this triangle, which means those would be corresponding parts. And then also, if these two triangles are congruent in the symmetry, these two angles would be congruent, and these two angles would be congruent. So we can say one diagonal bisects the angles. Right? You can use any of these in a proof just by simply saying if the polygon is a rhombus, then the diagonals are perpendicular. Or if the polygon is a trapezoid, then lower base angles are congruent. So all of these check marks translate into theorems that you can use. We are mostly going to be using these in solve problems, and the good news is we're going to let you use this table. We know this is a whole lot to remember. All right, I just want to show you two quick problems here. One is a proof and one is a solve. I know this is a little bit longer. We have A, B, C, D is a, I did not mean to put that bar up there, ignore that, is a parallelogram. Angle GHA is congruent to angle FEC. GHA, FEC. And HB is congruent to DE. HB congruent to DE, that's all given. I'm trying to get GH, this guy right here, and EF. So that leads me to believe I'm going after these triangles right here, right? That would help me get that. So I only have one piece so far, but I know a lot about a parallelogram. So if you have that little chart in front of you, or if you look back, one of the things I know about a parallelogram is that opposite sides are congruent. So I'm going to choose this side and this side. So I could say DC is congruent to AB. If I have a parallelogram, then opposite sides are congruent, and then I can subtract to get the pieces I want. EC and AH would be congruent, because if congruent segs are subtracted from congruent segs, then the differences are congruent. Now I'm really close. I have now this piece and this piece, so I have two angles here, and I have these two sides, so I'm missing one more piece. What else do I know about a parallelogram? I know opposite sides are parallel. So I'm specifically going to pick this side parallel to this side and use this transversal. And I hope as soon as I do that you realize why. So I'm going to say DC is parallel to AB using that property. If I have a parallelogram, then opposite sides are parallel. And why do I want them parallel? Because now I can get those two angles because they're alternate interior. That's what we've been doing so far. Angle ECF congruent to angle HAG. If parallel, then alternate interior angles are congruent. Then my triangles are congruent. That would be angle side angle. And then I have corresponding parts for GH and EF. If triangles congruent, then corresponding parts congruent. So anytime they give you a parallelogram in the given, they're giving you a lot of information. Every one of those check marks in that parallelogram column on the previous page, any one of those properties you could have used in this proof. We specifically chose opposite sides congruent, and we chose opposite sides parallel. Don't forget, parallel is important because it gets you angles. All right, ABCD is a kite. Angle CEB, this guy right here, is 15x. And angle ABE, this one right here, is 8x minus 10. And it asks for angle BAD, which is this one. So if you go back and you look at your properties of a kite, you should have realized that the diagonals are perpendicular. That means this 15x right here, I'm going to say diagonals, perpendicular, diagonals. Therefore, that 15x should equal 90, and if you divide, you get x to be 6. All right, well, how does that help? Well, let's find this angle. Angle ABE then would be 8 times 6 minus 10. That's 48 minus 10, which is 38. So now, if I'm just looking at this triangle, AEB, I know this is a right angle. I just found this angle right here to be 38. Can you find me this guy up here? Right? Wouldn't that angle be 180 minus 90 minus 38? If I solve that, I should get, what, 52? So that means this angle right here is 52. Well, how does that help me get this whole angle? Because don't forget, this is the one I need, this whole guy. Well, if you look back at properties of a kite, right, you can look back at that chart. This diagonal bisects these two angles. So this angle is congruent to this angle. So if this is 52, this is 52. So that would be 2 times 52, which is 104. Okay, that chart's going to be really handy. You're going to want to go back and look at that because I know all those properties of kites are not fresh, so keep that in front of you as you're working through these problems. Okay, and yes, you will be able to use that chart on quizzes and tests.